I invite Dr. Bobji to deliver his keynote address. Thank you.
Thank you, Rajendra Kumar. Thank you. Thank you, Rajendra Kumar and other organizers for giving me this opportunity to come here and visit this beautiful NIT. I have never been here. This is the first time I have been coming to Calicut, NIT Calicut. So today I am going to talk about the work which we have been doing for about last 10 years. It is on in situ transmission electron microscope as a new tribological tool to understand what is happening at interfaces. Okay, so Anant Iswara is my PhD student who is now in Canada, and he had done most of his work here in Indian Institute of Science, Bangalore. So I will start with a little bit introduction on Indian Institute of Science. Most of you may be knowing about IISc. IISc is one of the research institutes, very old, 100 years, right? What most of us may not know is it is modeled against on the premise of Nalanda University. Those of you who have read about Nalanda University in the history will know that it is about a closed university. It's an enclosed space, and then you are just invited and put inside. All your basic needs are taken care. That's it. You have not been told what you should be doing, what you should not be doing at all. You can do whatever you want, right? Only it is the environment is supposed to be so stimulating that it will provide enough intellectual inputs to you, and finally you will produce enough output which will be of use to the society. That is the basic principle of Nalanda University, which we try to emulate at the Indian Institute of Science. Okay, we have a nice campus. Rajendra Kumar knows well. He did a PhD. We had very nice time there doing PhDs. So we have nice campus. Food is taken care. Accommodation is taken care. Professors don't ask you to come to the lab and spend 20 hours a day. They just don't bother. That's a good and bad thing. And you have a lot of plenty of places to roam around and explore and things like that. You tend to make a lot of friends from various departments, various fields of research, and that discussion brings about like a true interdisciplinary research. Most of my research have been contributed by those kind of discussions, what we favorably refer to as a coffee board. So we have a small coffee kiosk. That's where most of the research goes on, and middle of the night, 2 o'clock. That's where it happens. And the original seed idea for this one came from Vivekananda, who is a philosopher, and Tata, Jamshedji Tata, who was a great industrialist of India early. During British times, Tata wanted to start a steel industry and he was not able to start it. British were not helping him. Rather than helping him, they were putting a lot of blockages in his path. So he decides to go to US and get the technology from American technology. So at those days we have to go by ship. So he was traveling from Japan to US on that through Pacific Ocean, and Vivekananda was traveling in the same ship. He was going to Chicago for international conference on religions. That is where they met on the ship, and then Vivekananda is supposed to have asked Tata, why are you going there? He said that I want to get a steel factory to India. And then Vivekananda said, you are giving Indians fish. Please teach them fishing, not just give fish. And that led to the discussion. And then it said that the technology has to be developed in India. That's the outcome, and IISc was the outcome of those discussions and deliberations that happened in the ship. In fact, when the IISc was formed, Vivekananda was invited to be the first director of IISc. which he promptly refused, saying that I am not a scientist here. You better find a better scientist to direct your institute. That's the letter, and we have that copy of that letter in our institute still today. Okay, so that is the history of our institute, the great institute. And we have about, it's a very small institute, as I was saying, we have only about 400 faculty and about 3,500 students. This increase in number of students happened recently in last probably 3-4 years. Before that it used to be stagnant at 2,500. When we studied 2,500 students, and the number of students remained constant. One of the pride we take is that the student to faculty ratio, right, is very small. Each student gets to interact very closely with the faculty. That's the advantage of ISC. We have mainly research students, and of late we have started undergraduate program. It's a different type of undergraduate program, because one of the mandate given to us is that show the way, lead the way. No? So we are starting an undergraduate program in science, not in engineering, science, because the quality of undergraduate program in science is not up to the mark. That's what many people felt in India. So we have started a lot of ICERs, IIC, Indian Institute of Science Educational Research Institutes. Along with that, we have started this undergraduate 4 years science program. Anyway, so this slide, I added it after the inspiring inaugural session. Usually inaugural session I don't I just hate, but today's inaugural session was very different. I get to know a lot of quotes, and this slide is a tribute to Professor Nambudri Path. Okay, sir. Because he reminded me of my professor in engineering college, who had inspired me, Professor Valliyappan. So he used to talk energetically, and the way he came to the dais just reminded me of him. So that is why I put this slide. I needed to explain. This is a tribute to all the teachers who had inspired me into doing research. So basically everybody asks, as a student, I also used to ask, what is research? Why do we do research? That's where we start. Now, when you come into IISc, they tell you, start doing this problem, that problem. My professor gave me a big paper, philosophical magazine paper. This is the paper, go read and come. That's all. We don't know what to do, when there are no courses to take. There is only few friends roaming around here and there. Everybody seems to be more relaxed and not seem to be doing anything. Some people are doing some experiments once in a day, and they never come to the lab also. So that led on to talking, and this slide took lot of time to evolve. It has taken probably 20 years for me to get this. So this is my view on what research is, and why this is important for me to explain why I am doing what I am doing. We even had yesterday some discussion with Professor Kim about what do you want to be, what is research, like why MIT is different from other places, right? So researchers, what drives them? Why we are not able to get similar drive here in other institutions around the world? Okay, intellectual, he agreed with me, I agreed with him. So yeah, intellectually everybody seems to be same. The students are having same intellectuals, but when they put in the environment differently, the output is entirely different. We have been telling about this about our IIT students. In India, if they stay back after their BTech, their output is very, very small, right, in whatever way. But the same person who goes to US, exposed to a condition in NASA golden days, now nobody is going to NASA, I am here from IITs, but those people who have gone abroad from IITs, especially to US, they have succeeded extremely well. Those who have stayed back, they also have succeeded, but not to that level. No, there is a clear-cut distinction when you go back and see.
They have succeeded in software industry.
Yes.
In India.
Right. So what is that? What drives that? That's what is the question is. So the way I see it as is, nature is very complicated. Okay, we all put it like a fire. No, it is boundless, shapeless. It is ever changing. So our aim is to understand what is the nature is. Why we want to understand nature? We can't ask such questions, I guess, because that is the curiosity. We are part of nature. We are not, I don't agree with artificial things, right? Everybody claims that it is artificial intelligence. How can it be artificial if it is created by the nature, product of nature? I am a product of nature. So I have to be, whatever I do is also nature. If I am killing the trees, it's the nature. It's my nature, right? So it is very difficult to understand what is nature. That is what everybody tries to do. Okay, why we don't know? There are mainly two ways of understanding the nature, right? One is through experimental observation, another one is through abstraction, right? Why we write big differential equations? Because that is where we try to understand our abstractions. Mathematics is the best way to abstract. We don't ask question why 1 plus 1 is 2. We stopped asking questions at the 3rd standard, 4th standard level in the schools because teacher told don't act smart, right? That's why, sir, we don't ask questions, right? We have been trained not to ask questions in the classrooms. So abstractions is the way where we cannot ask questions. It just comes. The apple has to fall from the tree and it triggers something, right? So that is what abstractions is. Experimental observation is always noisy. Any experiment I do is always bound to have some error, right? But without experimental observation, I cannot understand nature. Okay, what we need to get a complete picture of nature is that I need to combine these two. Abstraction is remove all the errors from the experimental observation and give you a nice theory. F is equal to m1 m2 by r square. Where is that square came from? Why r power 2? Why not? It is, the experiment will always tell you it is r power 1.9999 plus minus so many digits. It doesn't give you 2 exactly. But somebody has to come, no, it is 2. Once it has been told it is 2, and then every other experimental observations make sure, validates that. Yes, more or less it remains close to 2. Right? So that is the power of abstraction. We need to go beyond what we generally see. We need to understand things beyond what is visible to us, what our senses make sense out of it. That is the thing. So when we have these two, that is why we need models. Why do we need models? Because we need models to predict things. Ultimate goal of anything, understanding nature, is to predict what will happen. If I give this rose to my girlfriend, is she going to marry me? I need to know it beforehand, before I decide to give a rose to this girlfriend or that girlfriend, right? So we need to predict. That predictive capability comes only through models, right? Models are not at all accurate. We know models are all very, very approximate, but it gives you enough predictive capability. You know, this is the philosophy behind most of your video games, right? Nowadays you play, well, I don't know what you play, Temple Run? Yeah? No Temple Run. I think these are all, what? Temple Run, yeah. Candy Crush, Temple Run, Subway Surfers. If you see all these video games, you will see that there is an element of arbitrariness, randomness. But once the randomness is decided, you have been given some chances, right? You follow definite rules. If I push my finger up, the man or thing jumps, right? If I push it left, he turns left, right? You have been given control. But ultimately it is randomness which is producing whether the train is coming, whether the wall is coming to an end, whether there is a tree. Obstacles are random, but you have been given a chance to meet the obstacles, right? That small model, we need a model to predict immediately what happens tomorrow. I need to be able to catch my flight tomorrow. For that I need to know a model. I know this model, today I will give a talk and my talk will be over in 1 hour. I need to know that. Without that I cannot plan that I can leave tomorrow to Bangalore by plane. That is why we need this model. This model is just enough to give what we want in a very short span of time with a well defined things. Okay, why do we need model? You know, this is what is giving us intelligence. Why human beings are intelligent? None of the other animals can predict things. All this talk about cows crying before they are chopped off their head is all false. They have no way of predicting that they are going to be chopped. They happily go and then give their head, yes, please chop me. Right? They don't know. Only human beings, that ability to plan ahead, to foresee ahead, to predict, gives us everything. Anxiety. Huh? Why we are not able to predict tsunami is the question. Is that right? Right? That's your belief. I have to believe, no? It seems to be a belief. We don't have any experimental data. Please do an experiment and show me that it is true. Okay? With 0.99% correlation. Then we will talk about it. Right? We don't know. So what does models help us to be able to predict something? If we are able to predict something, what? We have to use it to make our life easier. Right? You can predict. I know this Bobji is going to give me boring lecture. So I can predict I don't want to go to his lecture. You can take a decision, right? So what helps us? You want to make yourself comfortable. How do you make yourself comfortable? You want a cell phone. You want to be able to play a video game when your professor is boring. Right? Without him coming to know. He thinks that he is writing notes seriously. But here you are sitting down and playing. So all these things is important. Helping you to deal with your life. Deal with your anxieties. Right? This is what we create products. Once we create products, the product is what is giving us money. Right? We generate wealth. So I put it as wealth because I am a researcher. I am also into this business. I create products. What is the product for me? What do I sell? What the professor sells? Knowledge. I sell knowledge. Is it? Okay. What is my product? Students is my product and knowledge is my selling things, right? So if I sell knowledge, what do I generate? Right. Do we generate? Those who have more knowledge will generate, get more money? Yes? True. It's true. IIT professor will tell it is false. BTechs will get more salary than MTechs, than PhDs. Agreed. Fine. It's all myth. Everybody has told you, go and study, you will get a job, you will make money. Right? Bill Gates did not pass the exam, pass his college. Right? Steve Jobs. Why? If you want to become Steve Jobs or you want to become Einstein. Why? Think about it. Right? What is that is giving you? What is the education giving to you? Education is not to create money. Knowledge is not to make money. Right? Go to MBA classes, they will teach you different thing. This is not MBA class. So think about it. This is only to stimulate thoughts. I have put it. Okay? Understand? Most of the people are working here. Salesmen. They sell something or other. Right? Very few people are here. Who? Engineers. This is salesmen. This is engineers. Here to here. Who are these arrows? India is very successful. Software engineers. They convert knowledge directly to wealth by selling services. Okay? And here comes, who does this? Researchers. How about the top one? Top two arrows. What is the difference between a scientist and researcher? Think about it. This is mostly done what we call engineering research or industrial research, and that is that basic fundamental research. Right? And when a scientist does this or a scientist does this, right? it becomes technology. This is engineering, optimizing our model to make money to increase the efficiency. This is what my tribute to my professors who have inspired me to do research. Okay, so coming back to my research, what do? I work in tribology. Everybody knows what is tribology, rubbing of surfaces. I didn't understand who was the organizing chair who had coined the word tribology in the morning. Okay. I thought tribology was given or at least popularized by David Tabor. Okay. So tribology is about rubbing two rubbing surfaces with or without liquid, air, gas, particles, anything. If you see that, if you want to understand this, you need to cross over so much of length scales, so much of time scale. Why? When two surfaces come in contact, the contacts occur at very small length scales. You can feel that when you bring two your hands too close to each other. Where are the contacts occurring? Not throughout your hand, somewhere tiny things. What is happening there is what is going to affect your friction. What is going to affect at what you see at macroscopic level. So you need to understand this whole thing. Now as it exists today, we have a model which spans, you see the diagonally. Very small scale, very small time scale, yes, we have molecular dynamics, right? Very big time scale, very large time scale, very large scales, we can build bridges, we can build Eiffel towers, no problem, we understand, and they will last for 50 years, right? So my aim is to push these things down, small scale, smaller time. Why? We want to understand what is happening here. How do we bridge this? How do we translate what is happening at small scale to a larger scale, both in terms of time as well as length? Okay, this is what the problem is. We want to understand friction. What is friction? Right? Most of the theories which you study in engineering, continuum mechanics, right? Solid mechanics, fluid mechanics, thermodynamics, everything is conservative. What is conservative? Energy is conserved. Energy is neither lost nor destroyed, right? But engineers know efficiency is always less than 1, right? Where did the efficiency go? Why we are not able to convert it to 100% efficiency? Thermodynamics will tell we can achieve thermodynamic efficiency by Carnot engine cycle. Morning there was a discussion about IC engines having 50% friction loss. Yeah, it is not 50%, it is less than 15%. Less than 15% because the efficiency of IC engine itself is 27%. Brake thermal efficiency. If you see about 30% is if your MFPI and all your modern technologies you have got. Right. Thermodynamic efficiency will be like 50-60%. So, but friction loss is very small in IC engines, right? The technology has improved so much, right? You can see now we don't have to change our gear oil. How many of you changed the gear oil? Two-wheelers gear oil, how long, once in how long you change? 3 months, he is from industry, he is lying. 6 months, lying. How long? When did you change? When I bought the bike in 1989, I had to change it once in 6 months. That is what they recommended. Now you don't have to. Right? I change the engine oil for my car only when I give for servicing. I give servicing once in 2 years. My car is 10 years old and it is running fine. And it is giving me 13 km per hour. So I have no problems. Under any performance criteria it is performing well. These are all some criteria which has been told by industry. You know, these models, the model is the problem. Predicting the life of this engine oil is the problem. Right? How do you know your oil is bad enough to change? Have you ever tried? What? If you do like this, it should be more sticky, less sticky. More sticky. Viscosity should be low. Think about it. It should become black. It should have enough carbon deposits that you will see it black, or it should have become very viscous. Then only you have to change the oil. Anyway, don't blame me if your vehicle fails down. Okay, please follow your manufacturer. Anyway, that is the question of reliability. That's where we are coming. What is the problem? Most of the scientists, what they do, all this process which you do not understand, we put it under a carpet. You give one parameter, coefficient of friction, right? Another one is like coefficient of restitution. We do not know why the ball is swinging in Calcutta when the breeze from Hooghly sets in a cricket match, right? Why is that Zahir Khan is not able to swing the ball, right? More importantly, our spinners were not able to spin the ball, whereas New Zealand spinners were turning the ball very nicely. Yes? No, we don't watch cricket also nowadays. What's... So these are the important things. We don't understand what happens between the ball and the pitch. When the ball is pitched on the ground, what happens there? Okay, we put one coefficient of restitution, it is not sufficient, because coefficient of restitution is going to be function of the soil, who cured it, how much of grass in it, how much of humidity, where the breeze is there or not, everything. So what is the point in putting one number which you cannot predict? So that is where we are coming. Can we understand all these details and get me, can you predict coefficient of friction? Can you predict coefficient of restitution? Yes, we can predict it for engineering. Our ISRO VSSC chairman said that yes, brutal force will help. Engineering solution doesn't need to solve friction. Only efficient things need. If your friction is there, just increase the force. If your chappal is wearing out, change the chappal. That's the solution which you have got. You just throw it and replace. Only in certain cases where it becomes very, very critical. But most of the cases we have the solution. If the bearing has failed, SKF will tell you replace the bearing. Right? Because otherwise, if you have a bearing which does not fail till your car fails, then SKF will run out of business. So we don't make bearings which will last long, right? Industry secret. We should not talk about it. So we come engineering problem. What is the advantage of reducing friction and wear? Yes, everybody tells we can billions of dollars we can save, but that's not important. You don't want to save money. You don't want to save energy. Okay? You want to waste more energy. You want to spend more money. Then your GDP will go up. Then you are told that you are one among the best nations in the world. Nobody talks about efficiency, right? American cars are inefficient. Tell me one process in America which is efficient, right? Why? It is moving very fast. It moves like cockroach, right? This is taken with a high-speed camera, so it's going slow. Look at this. What is happening? The bristles. How they are interacting. You can think each bristle is like an asperity, roughness of your surface. How the complexity is coming in. What is the time scale, length scale involved. This is what is making tribology interesting. That is why we are looking at what happens at the individual bristle level. If I can model that, I can model this behavior completely. It is a collective behavior which is coming out from the individual responses. So our objective is to understand the macroscopic behavior, which you see as finally as friction and wear or coefficient of restitution as a function of microscopic properties. What happens at the atom level? What happens at the grain level? And what happens in microseconds, nanoseconds? From there, I need to integrate the whole behavior into a macroscopic thing where I am interested in. I am interested in seconds, I am interested in meters. This is where most of the engineering problems needs to be solved. All said and done, we will make a nanotechnology, so everything can be done. But final product has to be handled by humans. It has to have some size, some shape. If any mechanical devices have to be built, they have to deliver some energy, right? That is going to be the ultimate limitation, energy density that a device can generate or produce or can withstand. That is going to be the limitation of how small things you can make. Okay, so that is why friction becomes important. So morning Professor Kim was indicating, like if you make a MEMS device circuit, it's not going to, conventional tribology is not going to work. They cannot withstand the energy intensity that has been generated due to friction, heat or the driving motion themselves. So you need to be able to dissipate those energies, right? So we need to get the friction as a sum of all the interactions that is going on. Like I said, what is the grass, how much of moisture is there in the soil, which direction the wind is coming, what is the relative humidity, all these things you have to know in order to be able to predict which way the cricket ball will pitch or move after pitching, right? Similarly, where is also a cumulative outcome of events that is happening at small scale. So the question which I asked Professor Kim was very specific. I wanted to bring it in here. So what is the wear rate of your chapel? How many atoms it wears for every step, right? You wear in 1 year, how long will you be walking? Your chapel lasts for 1 year and you don't throw it because it is worn out, because new model has come, right? Can you calculate and find out how many atoms are last per step? See that it is it. We are not worried about progressive wear at all, right? When you throw your chapel, when it has torn, when a big hole has come in the sole, right? That is when it is a failure. It's not because it is wearing. In fact, you want your chapel to be worn. When you buy a new shoe, you need to practice few days walking in it. After that only you will feel comfortable, because your leg has worn to accommodate the contours of the chapel. The chapel has deformed to accommodate the contours of your leg and the way you walk, right? Depending on that, whether right hand side has worn more or left hand side are worn more. I see big smile and big nodding of head, because they are more experienced with their high heels, right? Especially the one with the thin pointed leg. If you wear that, it's very difficult to walk, right? So wear place, because there is no space to accommodate your body's inaccuracies. That is the problem. So the whole aim, the question which we are going to ask, can we control friction and wear by tailoring geometry and the material property? Nowadays we can place atoms where we want, right? Whether he has shown, why you are looking surprised, right? We can create structures at atomic scales. We can change the material what we want. So the whole idea in future is going to be, can I tailor my chapel such that it never wears out? Can I build a bearing which will make SKF out of business, right? Right. This is what we do at microscopy lab. I have to call a force microscopy lab because we already had, by the time I joined, we had 2 tribology labs in our institute. I am a student of Professor Biswas, who had the original tribology lab, which he changed to nanotribology lab. And then my senior Satish, who is going to talk tomorrow, he came and he joined the institute, and he had taken the registered trademark of tribology lab for his lab. Then when I joined, I had to invent a name. So force microscopy is what I can come up with. Creativity is too low, right? So we do in situ TEM, which is what I am going to talk about. We do experiments inside transmission electron microscope. We also do microfluidics, in which we do understand what is happening at the interface between the solid and liquid, okay? And we do this nanoporous alumina, where we will be able to control the geometry at nanometer level. Okay, and we use the same thing to change the material property also. I will just give you an example, and then we do modeling as well. We said that no point in doing only basic research. You said that we need some abstraction, and converting that abstraction is very difficult. So we convert the experimental observations to a model that can be used in engineering. So we go in for this adhesive contact modeling. I have a student here, a professor from here, who is doing his QAP. I don't see him. Jaideep is not there. Okay, he is working on that area, trying to understand how van der Waals interaction will affect contact mechanics. Okay, the biggest achievement in that one is we managed to get this van der Waals interaction into a finite element framework. Atomic scale events are happening at femtoscale times, whereas continuum is happening at milliseconds, microseconds. So we managed to marry these two, increase the time scale, even though we see atomic behavior. We don't see individual bonds breaking and things like that. That is even smaller scale. But as long as bond is not formed, slightly far away, you have non-reactive surfaces, what will happen? We are trying to understand through this model. And then we have an atomic force microscope. We also look at biological nature. We are trying to understand nature. We do look at fruit flies. We do a lot of experiments with fruit flies, tiny flies. We look at their structure, how their eye structures evolve as a function of mechanical properties of the proteins that are inside the eyes, and as well as the muscles. Apart from that, we do some conventional tribologies also. Okay. So the basic thing which we do is understanding the surfaces. You need to understand what the surface is, and surface again is through surface roughness. The conventional way of understanding roughness is through assuming that height of the variation of the height from the mean plane is Gaussian. Okay, that was a big, huge group of people who have worked based on that assumption. Still keep working, but this kind of work, which is first published in 1978, shows that the amplitude of the roughness depends on the wavelength of the roughness. As you become smaller and smaller wavelengths, your amplitude even becomes smaller. This is a log-log plot, which means you will be able to clearly tell if I draw a picture in the board, right, whether it is Kanchenjunga or it is a fractured surface. Everybody on looking at it, if I draw some scribbles on the board, you know which is mountain. We have all drawn mountains like this. Asperities are large for a given wavelength. The height is large. Whereas at small scale, the height reduces compared to the given wavelength. So that is important. That's what we learnt it. So when we do rub materials, we will be interacting only with those smallest asperities. Even in your chappal is interacting with your floor, only small, the interaction will be happening at all length scales. Most likely the wear is happening at the top level, atoms, individual atoms are getting removed, except when there is a catastrophic removal of chunk of materials. Okay. So we realized that we can control this roughness by two processes. What this power graph is saying is that this is a ulta. This is frequency, this is frequency, this is wavelength. Frequency is 1 by wavelength. So x-axis is made reversed. So this power curve is, this is a measured curve, it is supposed to go like this. But what, by mechanical polishing, we will be able to control the amplitudes beyond certain length scale. Right. What our recent results have shown is that we will be able to control this roughness here by a different process, which is electrochemical polishing. So by combining electrochemical polishing and mechanical polishing, we have shown that we can generate very, very flat power spectra of the surface. Okay. So That is why we are interested in doing this size dependent properties. What is the, how this one? Size dependent properties is dependent on both on small scale material behavior as well as geometry. So we study the geometry using roughness, using atomic force microscope, how is the roughness is affecting the various machining processes affect the roughness. This is what we study using atomic force microscope. We need high lateral resolution. Whereas, forget about geometry, we just scale it up. To study two asperity interaction, what we do? We just blow it up. That's why we started doing this in Ranjit Kumar. Use a huge tensile testing machine to deform two spherical copper balls, hemispheres. Understand only the deformation mechanism. Don't worry about the geometry. Geometry is well defined. That is another way. And then I got into this nanoindentation, which is my PhD topic, which naturally led to seeing what is happening at that small scale. Today I am going to talk more about that, and also we will do pillar compression test. Individual, make a well defined small scale pillars where we study only the size effect. Geometry is again well known, and combine everything through modeling. We have to use this to finally industry wants to use this. Yeah, we want to generate wealth. I want to become rich, so we do modeling. This is what our controlling roughness has helped us to do, right? This is a porous alumina. You see, this pore size is of the order of 50 to 70 nanometers. They are holes, and they are about micron to 10 micron deep. We can control them, and this is what we managed to do in our lab. This is being done by chemists. Lot of chemists are doing, right? What we managed to do, because we understand the roughness so well, like electropolishing as well as mechanical polishing combined together, we were able to do it over a very large surface area. Now we generate this porous structure over centimeter by centimeter, uniform. Okay, this is the, you can see the pores. I don't think you will be able to see that. You can see it here, right? Using this, what is that? We have grown small copper pyramids. We use this structure to generate this. So we have very nicely controlled pyramidal copper structures generated on the surface, again over large surface area. All these things help us to do experiments at macro scale. How the small asperity will control this. Okay, that brings me to that why we want to do this experiment in TEM. One of the main problems in tribology is that we cannot see what is happening at the interspace. When two surfaces are rubbing, we cannot see. It's not visible. So people have tried to make many attempts by making one thing transparent and observe at the optical microscope. And there are people who are trying to look from the side using scanning electron microscope. But transmission electron microscope, since the electrons are transmitting through the material, we will be able to observe both the side surface as well as the subsurface simultaneously and see what is happening. Seeing is believing. So we do this experiment. This experiment is very difficult, right? This is the first experiment that is done in 1998 by a Japanese group, where they took two copper wires and then slid against each other. That's at atomic scale. I work at slightly larger scale. Okay. So what is a transmission electron microscope? So quickly, transmission electron microscope is just like an optical microscope only. Only thing is the source of image formation is electron here, not light. We use the wave property of the electrons to form images. So electron from a source is converged using electromagnetic lens onto a sample. If the sample is electron transparent, that is, typically the sample has to be extremely thin. Extremely thin is 300 nanometers for copper. For aluminum it is 800 nanometers, depends on atomic number. So you have to make it 300 nanometers thin. 300 nanometers, the width of the thickness of your hair is between 10 to 100 microns depending upon what shampoo you used. right, and whose hair is there, right. So you take that and slice it to get 300 nanometers. It has to be 10 to 100 times thinner than hair. The sample has to be made like that. Then only this electron can pass through the sample. When the electron interacts with the material, it interacts in many complex ways. Okay, all this interaction is carried by the beam which is coming out of it. The information is there in the beam. Again, we put a electromagnetic lens to make an image, okay, on a fluorescent screen. But the advantage of transmission electron microscope is I can choose what interaction I want to see. Okay, this is what helps us to do this. How much time I have got? 10 minutes. Okay. So that is the transmission electron microscope which we use to see electrons at a smaller length scale. Okay, so to do this experiment we had to build a instrument, that is we want to do a tribology inside this. So it has to be done on a sample which is 300 nanometers thin, and we want to bring the indenter from the side. This is 300 nanometers, we have to bring an indenter type and rub. Okay, so this is the device which I built at the end. It is manufactured by Govindaraju. I think he is there, yeah. He is from Magnum Engineers. I had a very long interaction with him from my student days. So without his help we would not have been able to make this precision device. Okay. Those who want mechanical engineers who can come and ask me later how it works and things like that. I'll just we don't have time. So simply we have managed to make a pen size 3-axis micro positioner that can position from millimeter range to nanometer, okay, in 2 stages. Just like rockets have many stages, we have 2 stages, one coarse positioning, one fine positioning. Fine positioning is finally achieved with the quadrant photodiode similar to atomic force microscope. And we have to worry about the stiffness. Tribologists, everybody knows, those who have worked in pin and disc and everything, they will know if the stiffness is not properly manipulated, if the sample is loosely held, what it will do? It will start creating noise, crich, 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 right? And everybody will run away from the building. It will create such a high frequency noise that you will feel very uncomfortable with. Okay, so for that we need to increase the stiffness, otherwise you won't be. I will give the examples of this one. Right, so let us see what these are the first experiments which we did. But we want to bring a 2 atomic force microscope tip and see. The advantage of having like a talk before me is like Professor Kim has introduced you to all these things. Okay, only thing is he did this AFM experiments, bring a AFM tip next to your flat and deform the tip and then go take the tip back to TEM and see. Now I am seeing how it is going to deform, how it is going to interact inside the TEM. Let's see. This, by the way, the top one is a atomic force microscope tip. This is interacting with a sharp tungsten tip. This is the picture which you have at low Mach. This is the tungsten tip which is made in the lab, sharp tip, okay, by etching. That is a AFM tip, atomic force microscope tip. But when we do the experiment, what happens? The TEM has lot of, it's a high vacuum, at the same time you have high energy from electron. So any dust particles that is present, typically oil from your vacuum pump, okay, they are very, very tiny amounts are present. They will invariably decompose and deposit as a carbon on the tip wherever the energy is high. So finally what we ended up doing is interaction between carbon and carbon, right, and we can measure what is the attractive force, adhesive force and everything, just by tracking how the tip is moving. The advantage of this kind of experiment is we have complete geometric characterization. We know how the geometry is. We can characterize, measure it, and then we can track, we can measure the force. Okay, fine. We can track along the videos. So we are measuring the displacements with the nanometric accuracies as it is moving. And then we know the stiffness of the cantilever, which can be measured again in TEM. Then we use that to get force displacement curves. Right. So let us see what will happen if we start sliding two tips to each other. Okay. Nowhere, because the forces are very small. You can see it just slightly jumps over. This is the experiment for the simulation which he has done. Only thing is his simulation of tip jumping over asperity in molecular dynamics were done at a time scale of few nanoseconds, whereas this is done at few seconds. This is a real time video. So interactions are going to be entirely different. Molecular dynamics cannot come to this scale, we cannot go to the molecular dynamics scale. That is the gap which we have got. Our whole idea is to approach from both sides, try to understand whether we can see what things are happening, whether we can understand the nature. Right? This is two gold tips rubbing against each other. Right? You can see I cannot cut the gold tip because the tip stiffness is low. When you make a tip, it is thin and long. So by rubbing, you can see both the things are moving together. The material which came out of the corner here, this is removed by gradual means over a period of time. This sliding I can repeat it many times. What is the experiment? You see this scale is about 50 to 100 nanometers, the tip diameter. You bring 200 nanometer tips close to each other with your one eye closed. You don't have a stereoscopic vision in TEM, right? That is like more difficult than putting a thread through the needle eye with one eye closed. No stereoscopic. We bring it to this, align it and rub it. So you need a high stability, and that we were able to manage to get it by making these devices small, extremely small. Whole device is like a size of the pen, which goes inside the transmission electron microscope, and it is in high vacuum. You can see there is no vibration. No, any TEM, or those who have worked in TEM, you know that you go and tap on the table anywhere on the room, you can see your sample vibrating. Right? They are vibrating of the order of hundreds of nanometers. We can't do experiments like that. It will be away. It will go out of contact. So these are all extremely difficult experiments which has to be done in the middle of the night when no lorries are going along the road of IISc. Right. So in spite of that, if the stiffness is low, so what? We can repeatedly do. We can do fatigue loading. We can rub again and again and again. Okay, and see what happens. This is a already deformed carbon tip, sharp tip, rubbing against a carbon deposit on again gold. This is gold, this is gold, this is gold, in between carbon film is there. So by rubbing again and again, I am showing after about 200 cycles, the carbon has suddenly catastrophically deformed. Once the carbon deforms, we have all the allotropes of carbon present there. From carbon anion to graphene, rolled graphene to entrapped carbon nanoparticle inside graphene. Most expensive way of making graphene. Right? So coming back to tribology, what we can do? This is, we wanted to do sliding experiments, reciprocating sliding, right? In aluminum, the sample is aluminum alloy, aluminum silicon alloy. So we bring the tip close to the aluminum, bring it in contact. You can see the contours are happening. That is because the sample is bending with respect to the optical plane of the TEM. Right. As we start moving, the bending is changing. You can see the fringes are changing. This is called bend contours. The sample is bending with respect to the incoming electron optical axis. Right. That causes this one. So at very low load, very low contact pressures, which we have estimated to be this one, very low contact pressure, no material gets removed. At about 1.5 GPa, we can see material being removed by layer, and that gets accumulated on the end of this one. Okay. So, what we can also do is we can measure how the oscillation of this amplitude is changing. What is this? I am taking a pen like this, I am moving it. I know how much I am moving, but this end is not moving by the same amount. It is moving less because of friction, right? This is a driven spring mass system with the base excitation, right? If you can use that equation, we can find out what is the energy, how much it is deforming. From there we can get friction. We can measure friction, how the friction is varying. Okay. So some of the, again Professor Kim had shown that you can use a micro balls, then we can reduce friction, right? When we started these experiments, we tried a lot of things. We tried to do nanoparticles deposited on the surface. We want them to roll. Okay, we tried everything, but the problem is nanoparticles are hard. Whatever may be, the even gold nanoparticles are hard because they are not deformable, because there are no defects in there. You cannot have a dislocation inside a 50 nanometer gold nanoparticle. So they are not spherical, one, they are angular because of the crystal structure, and when they start, when you try to roll, they just get impregnated into the material. They rather slide rather than roll. Rolling is very, very difficult. But this is by accident we did found out that if we keep on rubbing aluminium using tungsten, the wear debris get accumulated. You see this. This is like putting some chapati dough in your hand and then rubbing, right? So what we realized that we need very soft material, whereas in macroscopic world we want a hard material, the balls to be made hard in order to cause rolling, whereas there probably we need very soft material, softer than both the counterfaces, which can make it roll. Okay, as we said, this is all not experiments which has not been repeated in some other lab. It is done only in my lab. Okay, for us it is repeatable. Till somebody repeats it and then tells us that yes, it is true, then these things are very difficult to justify. We know that it is happening, we can see, right? So we can give, and we have measured friction to reduce, not drastically, but at least we can within our experimental error we can see a considerable decrease in friction once this rolling of the particles sets in. Okay. So this is what is showing how the friction amplitude ratio is inversely proportional to friction, how the friction changes as the wear debris increases. Okay. We can study what happens to the wear particle. This is the slow motion to show that the rolling is setting in. They just roll, join with other particles, agglomerate, dissociate and form many particles. You see that they are just like clay caught between your leg and the ground, or between your cycle tire and the ground. It's repeatedly getting smashed and this one. Okay, we can study different mechanisms by which these wear particles, these are the, remember these are the protective layers that is formed on the surface. Beyond this, no wear is taking place from the main material. It is this intermediate layer, third body wear is what is happening. They are getting, absorbing all the energies that you are putting in as a friction, or friction is coming from this. This is the interesting thing we did. We keep on doing this. We are putting in energy through friction. We can locally melt this. How do you know it is a liquid? See for yourself. Right? We are going to pull this liquid. liquid droplet is joining and merging and re-merging. This is what is called a liquid bridge experiment. Liquid is joining, now we are pulling slowly, the bridge is found. Depending on the viscosity, we can see when it will break. So by measuring the distance at which the bridge breaks gives us a direct means of getting a ratio between surface tension and viscosity. So this is the first experiment where somebody has ever managed to measure viscosity of 50 nanometers of liquid, 50 nanometer cube of liquid. As things are, we are doing the experiment, it is losing heat, it's becoming solid. So after few cycles we won't be able to repeat this experiment. So we do repeated rubbing again, melt it locally, again do this experiment. So we think this liquid is not aluminium, it is gallium. Our calculation shows the amount of energy we are putting in is very, very small, and then we don't expect the temperature to be so high to cause the aluminium to melt, but it is gallium which came from the sample preparation using focused ion beam microscope. So we have done energy loss spectroscopy in TEM which confirm that that droplet is rich in gallium. So it may be some gallium aluminum alloy or only pure gallium, we don't know. This tells us how the liquid bridge is breaking at different points. We can measure viscosity. I think I'll end with this, saying that this is this part of the world, I think many of you will understand Tamil, I guess, right? Kannal kanbadum poi kadal ketpadum poi thira visaritha arivademai. So whatever you see is not correct. So we need to understand what those images mean in the TEM, that we need to interpret and then understand and then translate to the macroscopic world. We have just scratched the surface. We have a lot of work to do. Thank you.
We have heard a very interesting talk by Dr. Bobji, starting from the very fundamental philosophy of rubbing possibly to the most sophisticated kinds of experiments that he has conducted and corresponding results. Now the for this open for discussion, if some questions can be asked by the audience.
In your rolling experiments of your particle, it seemed to me like the roll was the bearing part was the side part. In other words, the roll was borne by the side part, and it happened coincidentally that there was a particle at this gap. So the rolling action was created due to adhesion of the top surface and bottom surface holding a certain part and then relatively moving, so it has to roll. In other words, the rolling did not seem to be a result of load bearing and rolling as we would typically describe a roll or bearing.
Yeah. So the question is whether that rolling was, of course it was accidental. So whether that rolling particle took any load or not. Yeah, most of the load seem to have been taken by the main contact. Okay, since we observe some significant drop in friction, we think part of the load is being taken away from this one. These particles are formed there itself. We did not put it. Okay, whatever our attempts to put the particles, it did not work. This happened by accident. These particles got, see, as the wear happens, the wear debris gets pushed away to the side for the both ends. Suddenly some particles get dragged, possibly due to van der Waals, possibly due to the forces exerted by the electron beam themselves, by charging, local charging and things like that. So they get trapped into it, and trapping is not sufficient. They have to be repeatedly deformed within that gap, whatever is there, to get a nice ball like structure. But once the ball like structure forms, there is a accompanying friction. Whether we call it a ball bearing or not, whether it can be replicated in a bigger scale or whether we can replicate in a other system other than this aluminium. This is aluminium, not gold. Aluminium is a big question which remains to be answered. Yeah.
As you say, beside aluminium, is there any another material on which it can be processed? Like generally we don't
Okay, aluminum we chose because aluminum has low atomic number and it is metal, so we can afford to have a thick sample. Aluminum is always used in industry is a statement which you have to agree. Every IC engines are going to be replaced with aluminum engines. So this is like a aluminum silicon alloy which will be ultimately used in those engines. So it does have industrial applications, but yes, pure aluminum is what we didn't have any effect of silicon on this interaction.
I'm asking in context to steel.
Hmm?
Steel. Any other steel?
We haven't tried, but it can be done. If you want, you can come and try.
I think we can have just one more question. If there.
Huh? Expect what? What is that? Dissipating? We did not calculate, we obtained the friction, we measured the friction by assuming that it is a driven simple harmonic motion. We didn't put in any dissipation. Yeah, I'll discuss with you. Yeah, I know you will. Come on, you know that you ask your friend Anantishwara. I will discuss. I think it is not very simple. You have to write down the equation and tell it. There is no dissipation model that has gone into it. Yeah. I can't hear anything. I will go and give the mic.
Do we have any micrographs or photography of those layers?
Which layer?
We talked about the layer
Thin
form of
slab.
the surface, yeah. And what about the thickness?
Yeah, the question was that whether we have any pictures of those layers and whether we have measured. When we did the experiments, we don't know which is a layer, which is the substrate. We were not able to distinguish. There is no difference in there. All we know is after doing the experiment, when we did the yields experiment, we know there was a more gallium concentrated close to the surface than the far away from the surface, subsurface if you want to call it, you know. So from there we know that something has happened. So we assume that it is made of a different layer. We don't see the TEM does not give any difference in crystallography orientation based difference. Yeah, we were not able to see it. Yeah.
Thank you, Dr. Bobji.
Okay.
For a very interesting and informative keynote address. And we would like to give you a memento as a token of our respect and appreciation to you. So I request Dr. K. Aleshu, Head of the Department of Mechanical Engineering, to give the memento to Dr. M.S. Bobji.